Dear colleagues, my name is Alexei Kondurin. This lecture is about our future in space. We are human, we are curious, we like to go where no one stepped before. Space is exactly such field, where human traces couldn't be found yet much. How can we get there? I don't mean low Earth orbit, I mean far space, where other planets, other stars. Let's look from beginning a human space journey. Our space flights were started almost 70 years ago from such small spaceship. Tiny one-pilot cabin was turning around the Earth. It was perfect at that time. It was enough volume to survive in space for a few hours. Since that time, some different spaceships were built. You can see recent spaceships Dragon and Starliner that represent last generation of spaceship, planned to be used in next 10, maybe 20 years. Not much volume inside too. All ships are comparable with minivan like Kia Carnival, for example. Can you sit inside for a long time? Days, weeks, months? These ships are designed for short time flight. Most of them are used for low Earth orbit, only to deliver astronauts to space station and return. These ships have limited resources, limited time in space environment, low radiation protection for crew, limited volume and crew number. These ships cannot be used for long-term flights to other planets, for example. Another kind of space construction is a space station. This is Salute Station, as a basis for Mir Station and International Space Station. These stations have larger volume than the spaceship. Pressurized volume of Salute was about 70 cubic meters. It can work in space for years, provide better radiation protection for crew. The stations provide a human presence in orbit from 1970, about 50 years till now. Salute Station is one block. It was made on Earth and launched as ready-to-use construction with all pre-installed equipment, including life support systems. International Space Station consisted of some blocks made on Earth and launched to orbit in ready-to-use state. The blocks are joined together in orbit. It required multiple launches, own engines or external orbital carriers, complicated procedure of docking. Mechanical strength of blocks and equipment must be sufficient to survive at launch acceleration. The weight and size each block are limited by launch rocket. It took about 10 years to assemble it in orbit. Overall, it costed 150 billions in price of 2009. Total pressurized volume of the whole station, is about 900 cubic meters. The question is it enough? If you look inside of the block, for example, Destiny, it doesn't seem that too much volume inside. It is viewed as one car garage size, is it? Can we build larger station? It seems not. There is a fundamental problem. We make ready-to-use blocks limited by rocket ability to deliver the blocks to orbit. Following a tendency of maximal payload delivered or planned to be delivered to low Earth orbit, we can usually deliver 20 tons or 60 tons with heaviest vehicle now, or maybe 140, 50 tons in future. This is not much, not a principal difference. But do we need significantly more? If you look what must be done for a really big step in space exploration, we need much larger structures in space. For now, we cannot make large interplanet ship or station. We cannot place really large scientific or industrial equipment in orbit, like, for example, particle collider. We cannot build greenhouse to provide food for a couple of astronauts. We cannot provide sufficient radiation protection for the crew. We cannot make spaceship with artificial gravity. All these structures require much larger volume. We are restricted to go over the lowest orbit. We need permanent delivery from Earth. It is viewed like we are tourists in space, short-time visitors. To be settled in space, we need at first large greenhouse to provide food and to regenerate air and water for astronauts. If no greenhouse, it means that no deep space flights. It must be some hectares of green garden for each astronaut. If we need artificial gravity, we have to build large construction like Stanford Torus in orbit. All troubles with human health, animals and plants in microgravity will be solved. Finally, we need O'Neill Torus, big enough to put plants, animals, humans in artificial Earth. Then we can fly to other planets and stars. So we have to rethink all our space programs, put this goal and achieve it. And then we can really to be settled in space. How real is it? How far future is it? Let's look at tendency of hermetic volume of space constructions with time. The tendency follows exponential law. It means the large space construction of some 1,000 cubic meters pressurized volume is not far away from today. How can we get it? Can robots make it for us? Functions of robot in space was an observation and communications till now. Look, Lunokhod 1 created in the 70s and Mars rovers created in 2000s. A building process of hermetic constructions is much more complicated and not realized by robots on Earth. The motion in space environment is much more complicated than on Earth. I'm quite skeptical about robots in space for today. Human activity in space orbit is very limited. The problem is spacesuit. Simple operations take a long time, but a building process in free space is much more complicated than astronauts can do it in orbit now. Inflatable structures like Bigelow orbital modules are much more prospective. From 1960s, there were some projects and space experiments with inflatable constructions. Today we have the inflatable Bigelow module docked to ISS. But inflatable shell is soft and weak. The Bigelow module wall is about half meter thick. The module is not bigger than all blocks of ISS. The soft shell doesn't provide sufficient mechanical strength. In orbital speeds, a composite materials as a cured resin impregnated with fibers are more robust and preferable. I propose a principally new way, making in space, building in space. As we do it on Earth, if we need big building, we build it in the right place. We do not move the building from the builder factory. We build it where we need it, where we use it. Let's do it in space too. We have designed and proved this concept in many years. Composite materials, what we use when we fly with airplane, prepared with uncured resin, is prepared on Earth, packed compactly into container, sent to orbit, unpack, unfold, and cure resin directly in free space environment. Finally, we will get large, strong construction in orbit or on Moon or Mars. When the construction can be pressurized with air, the crew can install all required equipment, systems, space garden, and so on. We propose a wall consisting of prepreg with liquid resin that will be cured in free space environment. The prepreg is open to free space environment. It solves a problem with residual gas during the inflatable process, but it makes a problem of liquid components in vacuum. The hermetic shell provides a hermeticity of the construction. The top rear layer provides required temperature range of the wall and prevents sticking of the wet resin layers. The thickness of the wall can be 5–10 mm independent on strength requirement. The free space environment is characterized by high vacuum, space plasma events such as low energy atomic oxygen flux in lowest orbit and high energy particles, and irradiation from sun and from galactic from fast space. Temperature range between minus 150 up to 150 and microgravity. These conditions are destructive for any materials on the orbit, including composite materials. Because the curing reaction in composite materials is sensitive to the environmental conditions, we carried out a large number of experimental investigations of curing reaction in simulated free space environment, such as high vacuum, plasma chambers, and temperature variations, and in stratospheric flights. In experiments, we used a number of epoxy resins compositions from companies certified for space constructions, our compositions, which can be used in space, and model resins, which are important to understand physical chemical processes in composite materials in space. Different methods have been used for experiments, modern methods and equipment for resins and composite materials. Special attention was paid to adequate simulation of space environment in the laboratory. We investigated chemical transformations and mechanical transformations in the resin and composite under free space conditions. You see here methods we used in kinetic of the process. First important factor of free space environment is a high vacuum. Low molecular weight components can evaporate from the prepreg into vacuum. As a result, the ratio fiber matrix can be broken up to the case when the uncured liquid resin can completely disappear from the prepreg. Another danger is if the resin components have different vapor pressure. Then the ratio of active components, for example, ratio of epoxy resin hardener, can be broken and the curing reaction cannot be completed. If the evaporation is intensive or the resin contains a large number of solid air or gas, the resin can be boiled up to formation of foam structure in composite. All this effect can damage the composite. To get a strong composite, such effects must be eliminated. We investigated these effects theoretically to build different models of curing, diffusion, and evaporation processes. We investigated the evaporation processes experimentally. On the picture, there is an example of mass loss of liquid epoxy resin and hardener into vacuum under different pressure and temperature. This is an example of evaporation rates for different epoxy resins with different molecular mass distribution. We developed a combinatory model for epoxy resin curing kinetic, where we can theoretically calculate the molecular mass distribution of the resin during the curing process, evaporation rate during curing, and predict the chemical and mechanical properties of the composite under the vacuum. We have tested some commercial prepregs available on market. As you can see, some compositions evaporate fast in vacuum, but we found some compositions that do not evaporate at all or with very low evaporation rates. So we have now some compositions which can be successfully cured in high vacuum of the free space environment. Second factor is space plasma or space radiation. This is really a combination of different kinds of high energy particles and radiations. I combine it together as one factor because their effect on a polymer material is characterized as a radiation damage. As a result, the individual atoms or ions or even group of atoms are disjoint from the mother macromolecule of polymer, and they are called free radicals. Free radicals are extremely active species and react fast. Their reactions are called free radical reactions. These reactions can cause disjointing the macromolecule up to low molecular fractions or monomers, and polymer disappear, etched with time. Or these free radical reactions can cause cross-linking of macromolecules. As a result, the liquid polymer became a solid. Actually, this is great, because the curing reaction does the same. The liquid resin became solid. We consider the plasma factor can play a role of additional hardener. These processes are complicated and depend on kind of particle, energy, radiations, temperature, and kind of polymer. This factor is also a reason of material aging in space. You can see the macro photo of virgin composite on left, and the composite after exposure in low Earth orbit, some years, on the right image. The polymer matrix there is etched and cross-linked. We investigated these processes in space simulator in laboratory. These are spectra of cured epoxy matrix exposed in plasma. The etching of surface layer with damage of the chemical structure are observed. These are spectra of liquid resin in plasma. It was amazing. First time we observed the mixing processes in liquid under vacuum and plasma in such a way that the product of destruction are moving from the surface layer into bulk layers. As a result, the product of damage are collected in the bulk layer of resin. So the usual surface modification process in plasma becomes a bulk process. No one expected this, actually. On the other side, it means that the space plasma can influence on bulk layer in the uncured liquid resin. This is great. The plasma can cause cross-linking not only surface layer, but bulk layer too. And the same effect we observed when the plasma was applied to the resin during the curing process. At the beginning, we also observed mixing of the resin layers, but with time of curing, due to rise of viscosity, the flow of in resin was slowed and mixing process was stopped. The resin became solid. Analysis showed that the cured resin contained products of the curing reaction and the free radical reactions in whole bulk layer of the resin. Here you can see the result of surface plasma etching in solid resin. This is left image. And the result of mixing of the layers in resin during curing in plasma. This is right image. We investigated the chemical transformations in the resins. For example, these are quantitative results of curing kinetic of the resin in plasma. Black signs is the solid resin in plasma. Almost nothing changes. Green signs are the resin curing in air, usual curing. The red and blue signs are related to the resin with and without hardener cured in plasma. This is an example of hydroxyl group concentration in bulk layer of the resin. The same analysis we did for all chemical groups of the resin. As the result of plasma radiation damage, the cross-linking is observed in the liquid resin without hardener. The Gale fraction up to fully cross-linked resin is appearing. These were experiments on simulation of high-energy components of space radiation corresponded to far space flight conditions. In real prepreg, the additional cross-linkings give additional high temperature peak of the phase transition. So the composite cured under radiations is more stable at high temperature than the cured in air. The mechanical test of composite supports it. The composite cured in low energy and high energy plasma shows higher modulus than cured in air or in vacuum. Therefore, as we showed, there are two computational processes in composite during curing in space. Evaporation into high vacuum makes composite weaker, and space plasma makes composite stronger. This opened for us a possibility to cleverly manage the curing process in free space environment. Another factor is the temperature variations. Thermal transfer in space depends on radiations. Sun side of the space construction is heated up and shadow side is cooled down. The temperature depends on angle of incident, reflection, absorbance, irradiation coefficients, thermoconductivity of materials, geometry of construction, and thermocapacity. The temperature measurements gives a range from minus 150 to plus 150 degrees Celsius. The curing reaction depends strongly on temperature, of course. We investigated the dependence of the curing reaction on temperature and simulated the curing kinetic process on temperature regime in orbit. An example of modulus of composite materials in construction turning around the earth is shown left. For this composite, the heating by sunlight is enough to be cured only under sunlight at 1 turn around the earth. For cylinder construction, we calculated a complete trajectory of rotation, precession, that the sunlight is heating up the construction turn by turn. The full cycle of the curing process overall construction takes about 24 hours for this particular composite geometry of construction, top cover material and its orbit. Such simulations can be optimized for selected geometry, materials and flight regimes. Another problem, which is also important, is thermal stresses. Due to thermal expansion, the construction hot side is expanded and shadow side is cooled down and contracted. If the contraction is cured and turned around, the expanded side is contracted now, and the contracted side is expanded. The thermal stresses can be doubled. To avoid it, the curing regime must be optimized to achieve minimal thermal stresses. This is possible. There are also other aspects of free space environment with minor influence on curing process, but it needs also attention. We are working on it. Our flight experiments were done in stratosphere above ozone layer. We used helium balloons. Usually the altitude for such flight is between 25 and 40 kilometers. At such altitude, cosmic rays, vacuum, temperature variations are very close to low Earth orbit conditions, except of course microgravity. The price of such experiments is much lower than the space flight experiments. Also, no harsh requirements and standard for our materials and payloads in comparison with space flights on, for example, on International Space Station. First experiment was done in 3-day stratospheric flight from Alice Springs in Australia. The cassette with uncured prepreg with liquid epoxy resins, different resins, was exposed at 40 kilometers altitude. The post-flight investigations showed that the curing reaction due to epoxy group conversion didn't occur due to low temperature, while cross-linking due to cosmic rays was sufficient. It was flight experiment support of our laboratory experiments and simulations. In second flight from Adelaide, we provided correct temperature regime of the prepreg in flight, and for the first time we cured prepreg with liquid resin in stratosphere. After that, some flights were repeated to support this result. It was done in different altitude, under different sun activity, on day and night side. The effect of cosmic rays was provided clear. The tested composites showed different behavior as it was predicted based on laboratory experiments. What can we build with such composites cured in orbit? We optimize the size constructions which can be transported by modern space carriers, I mean mass and size of transportation container, provided sufficient strength holding atmospheric pressure inside and stable for minimum 20 years in orbit. We have got that the construction up to 100 meters and diameter of 20 meters can be built in the orbit. After complete curing in orbit, the construction can be pressurized with air and used as a frame for future space station or spaceship or space base or space factory and so on. The pressurized volume would be up to 7,000 cubic meters after one launch, one rocket with 20 tons of payload. Compare with total volume of International Space Station now, 900 cubic meters after 10 years of multiple space launches. This is big difference. If super heavy space vehicle will be used to deliver our construction, our containerized construction to the orbit, the size of construction can be increased. For example, the space vehicle delivered 500 tons payload would give us 4 million cubic meters pressurized volume. It can be used for artificial gravity system even, for large greenhouse up to 150 hectares plantation area or large space hotel or space factory. The internal structure of the construction can be done in many ways depending on future usage of the construction. It can be a big factory volume, it can be a large scientific station, it can be even garage for our modern International Space Station, which whole can be placed inside and pressurized. The large diameter of the construction allowed to install green area on external radius to get sufficient radiation protection for the crew in long space missions. Multiple launches with such curable large constructions docked together, as it was done for International Space Station now, can give us O'Neill torus. So with the same $150 billion, we can get it. And actually, how much does it cost? I take commercial price for materials, labor, research and launch. It gives me price of the large station about 1 to 3 billions in comparison with International Space Station of 150 billions. The same difference in price can be for Moon base or Mars base. The low price is due to much lower number of launches, no complicated docking unit and operations, no strong requirements for equipment, no expensive materials. We compare price for space factory based on Bigelow proposal for renting pressurized volume in orbit. You can see the difference. We compare price for space hotel based on Bigelow plans. Bigger business gives bigger income. It is clear. Large construction can be used for permanent space observatory with sensitive, serviceable, upgradable, expensive equipment with presence of crew. It will be different way for permanent scientific astronomical observation. It can be in Lagrange point or on the backside of the moon or in far space. So, we stay at the door into new era of space exploration. Thank you for your attention and welcome to future.